Welcome to video lecture number 6, which covers section 0.5, Algebra 1 Review, Variable Expressions and Combining Like Terms. Please take a moment to read today's objectives. This lesson begins with copying down some very important definitions that you will need to know throughout the rest of this course. We'll start with an expression. An expression is defined to be any numeric or algebraic phrase that does not contain an equal sign. So in red, separated by commas, you'll see several examples of what we call expressions. Notice some expressions, like the first two, don't have any variables at all, and then the remaining ones do have some variables. So an expression can look quite different, but the key is does not have an equal sign with it. Oftentimes, expressions contain variable terms. Variable terms are symbols, generally letters, that are used to replace an unknown numerical value. So in red, you see various examples, and different letters are typically used. Obviously, most commonly used as a variable in algebra is x. We could have variables with numbers, like you see 2z, and you may see multiple variables together, but all of these, because they contain at least one variable, are called variable terms. Expressions also contain constant terms, and those are simply numerical values that do not change. So in red, you'll see what are the constant terms in various expressions. So whether it's an expression that is x squared minus 4x minus 3, the constant value is only the number that's by itself. So there's no variable with it to be able to change its value. Expressions in variable terms often contain coefficients, and those are defined to be the number that is multiplied in front of the variable. So you'll see three different expressions separated by commas, and notice in red are what we would call the coefficients. So in the first expression, 2 is the only number multiplied by a variable, so it is our only coefficient. Some expressions have multiple coefficients, like the third expression has 2 coefficients. So depending on the size of the expression, it may have several coefficients. A nice easy way to understand how these four definitions are related are through this simple flowchart diagram I've created. So for example, suppose you have the expression 2x plus 7. Well, expressions are made up of variable terms and constant terms. So in that expression, you see the 2x is the variable term, and the plus 7 is the constant term. Now, variable terms also contain coefficients, and those are the numbers that are multiplied by the variables. So that may give you a decent idea of how they are related to one another. Objective number 1 is related to writing algebraic expressions from English phrases or words. So in example 1, you'll see various phrases written out, and our job is to convert them to mathematical symbols using variables and other numbers. So I'll pick a few of these at random to do, and then I ask that you try your own and have them ready to check in class tomorrow. Example 1c reads, the quotient of a square of a number and the cube of a number. So what I typically do in these problems is I work backwards. So I'll start at the end on the far right of the wording first, and then I'll just try to pick out specific chunks that I can convert into symbols one by one, and then I'll piece it all together. So I notice the cube of a number is x cubed. It doesn't tell us what that number is, so I'll use an unknown. The square of a number I've identified as y squared, and we don't know if these two numbers are the same. So notice I'll use a y for one and an x for the other. And finally, the quotient, meaning division. So when I piece that together, if I'm dividing those, I'll have y squared on the top. That's my square of a number, divided by, or the quotient, with the cube of a number. So my final answer for 1c would look like that. Example 1g reads, a company has a total of $1,000 to distribute as a bonus to its employees. How much money does each employee receive? So once again, I still will work backwards, and I've underlined in blue the question at hand here, and that's the most important thing. How much money does each employee receive? Well, it depends. How many employees do we have? Since we do not know that, we will use a variable for that, represented here. E will be our number of employees. So if we have this $1,000 and we're going to distribute it, we don't mean distribute as in distributive property. We mean evenly divide it up so every employee gets the same amount. So the operation that we're actually dealing with here is division. So distribute doesn't mean necessarily the distributive property in this case. So to find out how much money each employee gets, we will take 1,000 and we will divide it by how many employees there are. Now it says write an expression. All of these should not have equal signs, so we will leave our answer in this form. So again, please try the remaining exercises from example 1 and we will check them tomorrow in class. As we continue to equation solve throughout Algebra 2, you're going to run into combining like terms very often. So these problems that follow are associated with objective number 2 from our notes. So again, when solving various equations, you're going to have to combine like terms. And just to be clear, as it says in the second bullet, when we say combine like terms, we mean to add or subtract terms that are similar together. So combine meaning add or subtract. The first general rule you need to be aware of is that constants, remember we defined this earlier as constants just being numbers themselves, remember they can always be added or subtracted together. So even though 6 isn't identical to -6, they're both numbers in general. No variables, so we can combine them. So if you just go left to right, remember according to the order of operations, we would be able to simplify this simply by combining 7 minus 6 minus 4 plus 2. Final answer here would be -1. The next rule says variable terms must have all of the exact same letters in order to add or subtract them. So if you look at the expression underneath number 2, you'll notice that I have 2y variables and I also have a -x and a +x. So I've underlined the similar terms in red and in blue. So when I look, I say how many y's do I have if I'm adding them together, and that would be 2. I have 2y, so I would write it with a coefficient of 2 multiplied by the y. Now, with the -x, remember, there is simply a -1 in front of that x. We just don't have to write it there. And then there's also a 1 in front of this x. So coefficients of 1 are generally implied, but they are always there. So think about what -1 plus 1 is. Well, that cancels out to be 0. So there's actually 0x. And if there's 0 times x, that wipes away the term altogether. So in this case, the simplification of the expression would leave us only with 2y. Take a moment to try the next example underneath rule number 2, and I'll have you check your answer in the video right afterwards. Well, how did you do? When you look at my problem, I've highlighted in blue the like terms. Now, even though xy and yx are written in different orders, remember it's just multiplication, and we talked earlier that that is commutative. So it doesn't matter whether I write xy or yx, they are the same. And how many of them are there? There are 2. So we'll write 2xy. Notice the -yz and +yz cancel, and that leaves us only with what I've circled in purple. Now, there's not another term that is similar to it, so we must carry it down and the sign in front of it. So it's a -zx. So our final answer in this case would be 2xy minus zx. Rule number 3 states that variables and constants can't be added or subtracted together, or they cannot be combined. So notice I've combined what's in blue and red because those are similar. However, 42 and -2d are not similar because there is a variable with the 2 and not with the 42. Since that 42 does not have a variable with it, they are not like terms and they cannot be added together, so this would be our final answer. Rule number 4 states that to add and subtract variable expressions that have exponents, the exponents must be identical. So in red, notice the like terms are the 2 terms in red, x cubed plus x cubed. There are 2 of those. Notice we do not change the exponent whatsoever. It was x cubed. We leave it as x cubed. In blue, I've highlighted y squared and y squared. Those are like terms because the variables are identical, including their exponents. There are 2 of them, so that's 2y squared. Finally, -x4 is by itself. It's unlike the others, so it does need to be carried down, and our final expression simplified would be -x to the 4th plus 2y squared plus 2x cubed. Rule number 5 is probably the most important, and you've probably already realized I've used it in several of the examples already, but it says we only are to add coefficients when we're combining variable terms. So notice I went ahead and in this expression I've identified the like terms in green, blue, red, and black. Now I will continue to simplify after I've written them next to each other. 10 minus 20 is negative 10, and we have 4x cubed plus 3x cubed to come together to give us positive 7x cubed. So notice how we added those. I didn't change the variable at all, but what I did change were the two coefficients in front of it. I just added 4 and 3 to give me 7. So our final answer would be 2x to the 4th minus y squared minus 10 plus 7x cubed. You can have this rearranged in other orders, but as long as you have each of these with their signs, then you will have the correct answer. So in example 2, you're asked to simplify completely, and you'll find that you'll use all of those rules in conjunction with one another depending on the problem you're given. So I've started example 2D for you, and notice the first move I've made is to distribute the 3 on the outside. Now alternatively, inside of the parentheses, you could have chosen to combine the 7y and the 5y first, but you still wouldn't have been able to add it to the 6. So I just went ahead and distributed the 3, and what you see next is the result of that. Now I've identified in red the 3 like terms that remain after multiplying. So I have negative 5y, 21y, and 15y. So together that's going to give me 31y. And again, I'm just paying attention to the coefficients when I'm combining those. Notice I also have a positive 18. And since I can't add these together due to the y in 31y, then I must leave my answer in this form. Example 1H is a little more complicated because the coefficients, the numbers in front of the variables, are fractions. So I've circled in red the 3 like terms, notice, because their variables are identical. They all have just x cubed. So I went ahead and I noticed 2 of those 3 fractions already have a common denominator. So I went ahead here and I combined those 2 fractions by adding their coefficients. Since they have common denominators, I just add the top. Negative 3 plus 1 gives us negative 2. Then I went ahead and I carried down negative 2/5 x cubed. Now I have 2 coefficients that do not have common denominators. So we're going to have to find those common denominators. And notice the common denominator between 5 and 4 is 20. So I'm going to keep the x cubed with each and the signs all the same. Now, how did 5 go to 20? We multiplied by 4, so this would become negative 8. And 4 became 20 by multiplying by 5, so this becomes 10. Now I have negative 8 minus 10 essentially, and remember from our very first section with signed numbers that that would be negative 18. So I have negative 18/20 times x cubed, and don't forget that at the very beginning of this problem, this x to the 4th didn't have anything else like it. Since I can't combine it with anything, it needs to stay part of my answer. Now, the only thing that can be done in this problem is to reduce the fraction 18/20 by dividing both top and bottom by 2. When you divide both top and bottom of the fraction in red by 2, you end up getting negative 9/10. And then the x cubed, and don't forget the plus x to the 4th, and that would be our final simplified answer. So go ahead and please try the remaining exercises from examples 1 and 2 and have them ready to go to check tomorrow in class. So this concludes video lecture number 6, section 0.5. Please take a moment to look over the notes and come up with at least one question that you have from this lesson. That way you have something to share with your groups when we talk about group questions at the beginning of tomorrow's class. Once again, thank you for watching and good luck.